and welcome to this fifth lecture for our course blockchain and its applications. So, today's lecture is the third on the topic of basic cryptographic primitives. These are the concepts that we will cover in today's lecture. We will continue our discussions on cryptographic hash functions. We will look into what is meant by hash pointers, which are of real importance in blockchains. We will also talk about the concept of hash chain, and we will see how a chain of blocks, which in turn would mean what a blockchain is. It will tell us how to actually construct a blockchain, the technology behind construction of a blockchain. So, that is in effect a chain of blocks. So, how to construct that we will see in today's lecture. The specific keywords for today's lecture are as follows: hash functions, of course, that is what we are continuing. We will talk about hash pointers, we will talk about and introduce the notion of Merkle tree, which we will see later that the blocks in a blockchain, they are made up of these Merkle trees, and we will also see what is meant by blocks. Now, before I dive into today's particular topic of hash pointer, let me do a quick recap of what we have so far discussed about cryptographic hash functions, so that it is clear to us when we talk about hash pointers how it relates to what we have so far understood about hash functions. Specifically, we are talking about cryptographic hash functions. So, if we remember that a hash function, a cryptographic hash function, so loosely we call it as hash function in this context. We are always talking about cryptographic hash functions. So, the hash function, say we denote it as h, which takes a message, say m of any arbitrary length, and then applies that function h of m, and then what we get as output is the hashed value of the message m, also called the digest, say d. The properties that we have studied before, which will be used in today's lecture, is that this hash function is a one way function. That means, from h, if I on m, if I apply h and get d, knowing d, I cannot get back to m. So, that means that inverting the function, let us consider that is impossible. Second property is that it is difficult to find two messages m1 and m2. So, that h of m1, if I call that as d1, and h of m2, if I call that as d2. So, if m1 and m2 are different, then d1 and d2 are also going to be different. It is very difficult to find two such messages m1 and m2 for which the digests d1 and d2 are the same. So, conversely, if there are two digests d1 and d2, if they are same, then we consider that the corresponding messages m1 and m2 are also same, although we cannot get back m1 and m2 from d1 and d2 respectively. Similarly, if d1 and d2 are different, then we can say that m1 and m2 were also different. So, these are some of the properties which are of importance in today's discussion. We will also talk about the puzzle friendliness property that we have seen before in the context of how it is used in blockchain. So, that is the background we need before we start today's discussions. So, today our first topic is what is called a hash pointer. A cryptographic hash pointer, often also called hash reference, and let us again call it as hash pointer for simplicity, but by that we will be meaning as cryptographic hash pointers. So, it is a pointer to a location where some information is stored. That is the first definition of a cryptographic hash pointer, or first part of the definition of a cryptographic hash pointer. Of course, any pointer, as we know that a pointer points to a particular location in maybe in memory where something is stored. So, of course, cryptographic hash pointer in essence is of course a pointer in the first place. And then the other important property is that the hash of the information is also stored. Okay. So, it is not only that this pointer points to a particular location, but also along with that pointing to the location, it keeps a hash of the information that is stored in that location. So, what are the uses of a hash pointer? As we can see very simply that of course, the basic part is that we have to be able to retrieve the information, that is the first part, that is very important, and definitely that is the use of a pointer, that we should be able to retrieve the information as shown here. And also, and that actually links this first point with the second point, that is that we can also check that the information has not been modified. Okay. So, it is not only that I can go to the location which is pointed by the pointer, but because I have kept a hash of the information which was stored initially, now we can check that the information has not been modified, or whether it has been modified. Now, how do we do that? And that is what is written in bold highlight here, that by computing the message digest and then matching it with the digest of the stored value that was there. So, let us give you an example, that suppose I had initially had a location where I had stored information about say data or a message, say m. So, I had this m. What I did was that I computed its hash and I got say this hash value d. So, in the location what we did was we are pointing, this hash pointer is pointing to that location, and also it has stored this hash, that is d. Now, say later on I try to retrieve the information which is d, that is what we want to retrieve. Okay. And then if we want to retrieve it, then what we will do? This pointer will go to that location and get the value that is stored. Now, if we have kept the value m, as along with that also we had the digest d stored in that location, then what is the advantage? If I go and try to fetch the information that was stored, I will get m. Okay. But how do I know that it has not been modified in between? I can do so by applying the same hash function on this value that I am able to retrieve by going to that particular location using the pointer. Then I can compute its hash and check if that is matching with this hash that was stored, or it is not matching. That means that whatever this m that was there that I am now retrieving, I apply hash on that and see if this is matching with the digest which was also stored along with the data. Now, of course, remember that from this h m I cannot, or from m I cannot invert and get back d and try to match it, because by definition these hash functions, these are irreversible. Okay. So, it is important, as you see what is written in bold, that I recompute the message digest and then try to match it with the digest that was stored with the original hash value. If they match, then I know for sure that the data has not been tampered with in between, and this is happening because of the properties that we have just now explained and which we had studied in our earlier lectures. So, if we have a pictorial description of hash pointer, as we see that this is the hash pointer which points to the data, as we have already said, and also the hash of the data that is kept. So, this is what we talked about in our previous slide, and of course, that should be reminding you of a linked list that all of us have studied in the context of data structures and programming and so on. So, it indeed is like a linked list. So, what we could do is that we could have this hash pointer kept in another block of data and make it point to this data as is shown here, and then the next hash pointer we can make to point to the data which will be comprised of this hash and some more information. So, and with that we can proceed and have more and more nodes in this linked list. So, it looks just like a linked list, but inner linked list from one node to another, and let us consider it is for the timing it is a singly linked list and it is non-circular. So, let us consider simpler versions of linked lists. So, what we have is that using this notion of hash pointers we can construct a list of such data connected together, but the added advantage is that if there is any modification to the data made, then it will get detected when we are going to follow the pointer and trying to get back the data that was stored in a particular location. Of course, that means that once we have stored the data, if the application requires it to be modified in between, this is not going to really help in the process. Rather, if we have an application where we will store data so that the data will not later be modified, but it can be checked whether it has been modified and it can be retrieved later following the pointer, then that would typically be an application where there will be meaningful use of hash pointers, and indeed blockchain is one such application, as we will see very quickly. Now, this is a way to show you how this tampering of the data gets detected when you are using hash pointers. Say I have this data which is this hello world as is shown here. So, this is the data or the message that we have here, okay. And then this is the hash pointer R1 pointing to this data, and remember that it also maintains a hash of this data or the message hello world. Now, here in the second sub figure, what we see is that from the original one where we had hello world followed by the exclamation mark, now it has been changed with the question mark. So, that means the data has now been changed from this hello world here, we have a change to this hello world here where we have this question mark, and that will cause this hash pointer to so called break. So, that means that now I can, if I follow the hash pointer, I will see that hash of this hello world question mark is not matching with the hash of the hello world exclamation mark that was stored in the hash pointer. So, that means that there is a mismatch between the two digests, what was the original digest and what is the current digest, and hence we can detect whether the data has been tampered with. Okay. So, that is the main use of a hash pointer, and suppose there is an attacker or an adversary who actually did this change from hello world exclamation mark to hello world question mark, and then we could always detect it. But if the adversary is smart enough, what the adversary would do is that not only the adversary will change this from exclamation mark to question mark, but indeed will also change from this R1 which is in this grayish circle to an updated value which is this R1 in this black background circle. Okay. That means that not only is this data changed, but also its hash has been changed. Okay. So, now if I want to figure out whether there was any tampering of the data, what I will do is that, not knowing that this R1 in gray circle has been changed to this R1 in black circle, I will try to follow this hash pointer which is this on the right, and there what I will do is that I will follow the pointer, get hello world question mark, and then apply the hash function on it. The digest that I get, I will try to match with the digest which itself also has now been updated. And now, because this also has been updated, although hash that was stored here would not have matched with the hash of hello world question mark, but this hash which is this R1 in black circle will now match with the hash of the hello world question mark. So, in that case the tampering will not get detected, but remember, for that the attacker will have to not only change this data here, but also the hash pointer accordingly. We will come to that and see how we can deter the attacker to actually make those changes as well. But if we consider some sort of such analogies in real life, you can think that if you go to any departmental store, say where you have to, or to a library for example, where you have to keep your bag and the person there, maybe the security person, will keep your bag in some locker there and give you a token. Okay? And in the token it is written what is the number of that locker. So, say the token number is 5, means my bag was kept in locker number 5. So, later on when I am trying to retrieve my bag, once I am done with my studies in the library or my shopping at the departmental store, what will happen? I will again now present the token which shows 5. So, that is like the pointer pointing to that locker number 5, and the security person will be handing me over my bag. So, that is like a normal pointer. But what if somebody replaces that bag, maybe it was a backpack which was changed to a handbag, then how can I prove that I had kept a backpack and now I am being handed over a handbag? So, there is no way to prove it, unless in the token that was given to me it is written that I had kept a backpack. So, if it is token number 5 and backpack, then later on when I present it, of course, that would mean that I cannot be handed back a handbag, I should be given back the backpack. But then of course, if that backpack is replaced by another backpack, so if it was a red backpack and then replaced by blue, so we have to give all such details. No one can actually tamper with it. So, here this backpack or red backpack etc. So, these are like keeping the hash of the data along with the pointer. So, that is an analogy you can think of, and you can also consider other analogies in order to see whether you have understood this concept of hash pointer. Very good. Now, as we said in this slide that one adversary has to change not only the data, but also the hash pointer. Now, how can we make this tampering more challenging computationally? Okay. So, what we do is that when we calculate that hash value of the data, it is not simply the hash of the data. So, anyone knowing how to calculate the hash of any data, because the hash functions are widely known, it will be easy to update the hash pointer including this hash value. Okay. So, what is done instead is that while generating the hash values on the data, we put certain restrictions. That means the hash values should be such that it has certain properties. And how is it done? So, along with the data, we say that there will be another piece of data along with the original data of the message. We will have another piece of data which is called nonce, means number which is used only once. So, that this concatenation of this data with the nonce, on that if we apply the hash function, I will generate a hash value which will have certain restrictions. Okay. So, let us see that if we put restrictions in a proper way, then it will be computationally challenging to recalculate the hash values by the attacker, as we tried to explain here by updating that R1 itself. Okay. Now, we give some example that if we have say nonce is say 0, then the text to be hashed will be hello world. Say if the hello world exclamation mark is the original data and then the nonce is 0, then hello world exclamation concatenated with 0, if I apply the hash, I will get an output. So, some example such outputs are given here, and we will also see by going to this particular site that how it can actually be done. So, let us go to this particular site, which is again the site which is given in the book. So, we give something like say hello world, okay, and then we can of course see how to calculate the hash value. Now, what we do is that we go to this third link, where what we do is that we give hello world, okay, and then I give a nonce of say 0, okay, and say I click on this calculate hash value and we get this as output. Okay. So, there is nothing unusual about it. You have the data, you append a nonce to that and you can calculate the hash value, it immediately gets calculated. But on the right hand side, we see that there is a restriction that we are putting, that number of leading zeros, that means the number of hexadecimal digits from the left, that will have that will be taking value 0. So, how many of that I would like to put as the restriction? Here it is written leading 0 is 1. So, you see that if I put a nonce value of 1, my restriction is not satisfied. Suppose I put nonce value of now 1 and I say calculate hash value, I get an output. Again there is 3 as a leading hexadecimal digit, and hence it does not satisfy my restriction of number of leading zeros to be 1. I try with 2 and then I again click on calculate hash value, but again I do not get the satisfactory answer. That means the first hexadecimal digit is not 0. Now I try with something else and then I click it, and then also I am not able to get the correct solution. Okay. So, then if this particular site that let us use this solution that it says solve a hash puzzle, and it shows that if I choose a nonce of 3, indeed if you see the output, the first hexadecimal digit is 0 and it is satisfying this requirement that number of leading zeros is 1. But you see that it was done very easily. I tried deliberately with 1, 2 and so on, and 11 I skipped 3, and if it was chosen as 3, I would have got the correct answer. But now let us change this number of leading zeros to 2, okay, and then I try to solve the puzzle, and then it shows that with a nonce of 57 I get, you see, that 2 leading zeros. So, this is what is meant by leading zeros here. And then also you see that I had to sequentially go from 0, 1, 2, 4 up to 57 to get the solution. Now, if here I change number of leading zeros to 3, okay, and then I again try to solve the hash puzzle, and then it is shown that at 614 I get the solution, and you can see that there are 3 leading zeros and so on. Now, if I try say 5 leading zeros and try to solve the hash puzzle, okay, so then what is happening is that now you see that it is taking a lot of time. Okay. So, what it means? It means that if indeed that we are trying to solve the hash puzzle with more number of leading zeros, it is you look at this example that I have got now the solution after some more time. You see that initially it was very fast with 1 leading zero, then a bit more with 2 leading zeros and so on. As I set 5 leading zeros, you see the nonce came up to be this 1006908. So, you see that from 1 all the way to 1006908, one had to try to get back to the solution, and as you put more and more such leading zeros, it becomes more and more difficult. So, that is the point that we have been trying to make when we talk about this notion of restrictions on the hash value. But at the same time, we also have to remind ourselves that this is happening because of the property of puzzle friendliness of these hash functions, and it is that puzzle that we had been talking about in our previous lecture, that we are saying that with the data what that I have to concatenate with it, so that hash of that will result in certain values that have certain properties that we would like to impose, which are these restrictions that we talked about, and typical the restrictions that are made in the context of blockchain are about the number of leading zeros. And by this example, I believe all of us have understood what is meant by these leading zeros. So, you see that there were 5 leading zeros as the restriction as mentioned here, and we got a solution where there were indeed 5 zeros. You can try yourself by giving more number of leading zeros here, and you will see that the problem becomes more and more challenging computationally, means it is going to take more time, and that means that here in the context of hash pointers, if we said that see it is not enough that on the data itself you calculate the hash and then you create the hash pointer, rather with the data you have to come up with a nonce, so that the hash of the data plus the nonce will have certain restrictions, like say 10 leading zeros or something like that. In that case, this hash pointer will be more difficult to compute, and not only it will be difficult to compute initially, but also for the attacker to change it will also take time. It will depend on how much computational power the attacker has, and also we will see that we will make it more complex for the attacker by adding more number of such pointers in a chain, so that a lot of effort would indeed be required by the attacker to tamper with the entire data. And that is what is shown here in this example, that now we are connecting different such blocks of data using hash pointers, and we form what is called a hash chain. So, if you see here that we have the data here in this first block, we have the data which is this one, and we have its hash which is this one, which is the hash of the previous block. So, let us have this example. So, we do not know about the previous block, that is I minus 1th block. Let us see from this ith block to the next block, which is I plus 1. For the I plus 1th block, the hash will be hash of this data, but this hash is not going to be simply the hash of the data, but it will be a hash which will also have certain properties like the restrictions we talked about in the previous slide. And then with that, from d I plus 1, I also have a d I plus 2, whose hash pointer will be pointing to this data. Okay. And then in the process, what is happening is that if say an attacker wants to change the data here, attacker will have to change this one, and if you see, this hash is the hash of this whole thing. Okay. So, if this is changed, then unless this is changed, it will break, like the example that we had shown here, okay, in the previous slides. Okay. So, that means that for the attacker, in order to get away with those tampering, they not only will have to update this hash, it will also will have to update this hash, and if there are more such blocks which are connected like this in a chain, all of these will have to be updated. And if you have seen in the example that the restrictions, if they are put that we need several leading zeros, in that case, for calculating each of these hashes once again and setting them up in such a way that the tampering cannot get detected, that will take a lot of time. So, we are trying to ensure that it is computationally very difficult for the attacker to do this. So, what we will do is that we will now move on to the next slide, okay, where we will see another application of these hash pointers, and which is what is called a Merkle tree. Now, in a Merkle tree, what we have is that it is a binary tree, as we all know. What is done is that there are, say, several such transactions, okay, say T1, T2, T3 and T4. What we do is that we calculate hash of each of these transactions first, and these are stored in the node. So, this first leaf node stores the hash of T1, second one stores hash of T2, third one stores hash of T3, and likewise for the fourth one. And then one level above, what we have is that this is a hash of these two. So, H00 and H01. So, in the next level we have hash of H00 and H01 concatenated together, and likewise for hash of 10 and 11 which go there, and we calculate this H0 and H1, and which in turn will go, and then we will calculate hash of that in the root. So, that is the root hash, or it is the Merkle root, which is the hash of all its next level of children, and then the next level, and so on. So, you see that it is like that hierarchical hashing that we had talked about in our last lecture, and then we get what is called the root hash, which is called also the root of the Merkle tree. And this is a way in which we organize hash pointers in a tree, and as we will see later that these Merkle tree is what is used for storing what are called transactions in blocks in a blockchain, and then we try to ensure that the blockchain is tamper proof by calculating keeping this hash of this root hash, that is the hash that is stored in the root of the Merkle tree, that is the H root, and then along with that we add some more pieces of information and create hash of that, so that changing that without getting detected will indeed be computationally very, very difficult. So, that is what we will see in our later slides. So, just a brief glimpse of that. So, in a blockchain which is organized as a hash chain, it will have these different pieces of information. So, each block will have a block header, it will have previous hash, the Merkle root, as I said, the hash of this block itself, there is a nonce, and then they will have the next block which will connect to this block using this pointer as is shown here, and this again will be connected to this as through the hash pointer. So, effectively we see that a blockchain will be like a hash chain where different such blocks will have different pieces of information. So, there will be a lot of information here, and this is only showing the block header. So, the block itself will be like this block header along with some more information in it. So, which will be those transactions, and these will be connected in a tamper proof manner in a hash chain, which is what is a blockchain. So, later on when we talk about the elements of blockchain, we will take up from this topic and we will try to remember that a blockchain is a hash chain where different blocks will be connected through hash pointers. So, that is what is the set of topics we decided to cover today. So, in conclusion, we have discussed the basic concepts of hash pointers. We have seen how it makes data tamper proof. We have seen how to construct a hash chain and define the Merkle tree. Also, what we have seen is that how a chain of blocks can be constructed using this notion of hash chain, and then we have seen that what each block typically looks like, especially what is the rough content of its header. We have not yet gone into the details of it, but given some glimpse of how to understand that how a block header looks like and how they are connected to each other, so that it will be tamper proof. And again the same set of references we have, the book on blockchain basics and the concepts of these hash functions are there in the book on cryptography and network security by William Stalling. So, that brings us to the end of this lecture. Thank you very much for your attention.